to do that because this video is really cool. So I'm going to stop this recording and see if I can get the video to play a little better. We'll see if we can start it again, because this usually works better than that. So, yeah, it's already working better. It's a cute little computer and it does really well on airplanes, but you can't ask too much of it.
Can I ask a quick question? When you say mirrors,
I'm going to be showing you the mirrors in a little bit.
Okay, but they're not they're not optical mirrors.
Well, they're X-ray mirrors, of course.
Okay,
this
all right.
is an X-ray satellite.
All right.
So, maybe it's just an interaction with the projector. That's interesting. This has always worked so well. Well, we'll just keep our fingers crossed that you can actually see the mast expand. It's jumping around instead of running properly. So I don't know. Anyway, you can see it come out, even though you're not going to see the animation work right. But it's all folded up, and it comes out one section at a time and locks into place until it's finally all the way out. And so, one of the things I brought for you tonight, and I'm going to give out afterwards, are brand new, hot off the presses paper models of nustar, where you can build a model of it, including the expanding mast. Limited edition.
Yeah, we use those to look for black holes?
Yeah. I'm not sure. Yeah, I don't know about that. You can look. I don't think you'll see any. Okay, so how do X-ray mirrors work? How do you actually focus X-rays? I'm going to assume that you all know how you focus visible light. Well, X-rays, you can't just bounce at normal incidence off of a piece of glass because they'll just go right through the piece of glass. So the first thing is you have to have special coatings on the mirrors. In the case of Chandra, they used iridium. In the case of nustar, they're actually multi-layer mirrors that are coated with, the outer 44 shells are tungsten and silicon, and the inner shells are platinum and carbon, and there's 133 layers. So these are all nested mirrors here. This is a cutaway view. And so you make these mirrors out of a special material, and then it's like skipping stones on water. So you don't go at a normal instance, you go to grazing incidence, and it just skips along and bounces to the next one, because if you come in too steeply, it still will go in, and then you won't, just go through instead of skipping and bouncing. And you have to bounce it twice to get it to come to a good focus. Wow. And it takes about 10 meters worth of travel before you'll get this converging beam. And so that's why nustar had to be so long, but because it was a small, cheap satellite, you couldn't build it that long and launch it in a shuttle like Chandra did. It's about the same size as Chandra's, also about 10 meters long. You had to launch this small, compact thing and then use this new technology to expand it so the detectors were down here and the mirrors are down here.
I was wondering what type of resolution can be obtained with that glancing?
Yeah, well, in the case of Chandra, which uses the same principle but different materials and has even more highly polished surface in here with less surface irregularities, they get better than an arc second.
How much? Better
Better than an arc second in the case of Chandra. nustar doesn't do that well. You'll see the pictures are a little blurry, but you can resolve things. So it's it's not as blurry as the gamma ray satellites that I work on. So it's tens of arc seconds.
Can you briefly describe how they actually test the optics for the mirror on Earth?
Yeah, it's let me just
you're talking to an audience of telescope nerds.
Let me just show you the picture. Okay, so here's a little better picture of it. So you can see these mirrors, right? Here's all the 133 layers, and they made them in segments. And so what they did was they had these molds for each of the concentric rings. They had a mold with a different shape. And then they had glass, and they slumped it over the mold. And so they made all these little pieces, and they had all these rigs, and then they put all the little pieces together. And, and they all had to be coated, so they had special ovens that they used to put the coatings on the pieces before they then assembled them all.
Wow. Did they actually...
So you can go to the nustar website and see pictures of them doing the slumping and putting all of these segments of the mirrors together. Like it was done at Columbia University in New York, actually.
Did they fire like X-rays down it to test the construction?
Once they put it all together, then they calibrated everything. I'm sure they calibrated some of the individual segments, and they made extra segments and tested them all. But it was it was very interesting and involved. But because they used conical sections instead of Chandra, which used more precisely hyperboloids and paraboloids, it was a lot cheaper to make because they could just make these conical sections of the different radii for the concentric spheres and just do this one thing, instead of having to actually grind things to these much more complicated geometric sections like Chandra did.
What's the effective aperture?
That's a good question. I'll have to think about that. It's got a pretty small field of view. Compared to Fermi, which I'm more used to talking about. So the detectors on the focal plane are these arrays made of cadmium zinc telluride solid state detectors, which it's a combination of materials that's well known to be very good for hard X-rays. And so this is a 2x2 array of those detectors. Each detector has 32 by 32 pixels in it. So it's not megapixels, right? But it's still, an imaging detector. So that's just one of them. And so now we'll talk about science a little bit. So here are the things that nustar's been trying to figure out. How are black holes distributed through the cosmos, and how do they affect galaxies? How do stars explode and forge the elements, and what powers active galactic nuclei? I'm not going to talk about number 3 very much. I'm going to mostly talk about 1 and 2, and I'm going to show you some of the pictures that nustar has taken and some of the science results that have been published so far. So this is one of the things that they're doing. They're surveying the galactic center and studying all these different places in the galactic center, including, of course, our very own black hole, Sagittarius A star. And because of the resolution, so this is degrees on the bottom here. This is about 2.5 degrees across here. They'll be able to look at different fields in all these different places. So that's a good answer to your question. Maybe 0.5 degree. So here is an X-ray image of the galactic center. There's the infrared view. So zooming in here to where Sagittarius star is, here's an image. And they looked at it for about 2 weeks, and they actually saw a flare coming from our very own black hole is at 8 something there while they were watching. The flare lasted for a few days out of the 2 weeks that they were looking at it. And that was sort of the first time that they looked at it, and they got lucky and caught a flare. Our galaxy's black hole is really pretty quiescent compared to big active galaxies that make huge flares and that last for months and get really, really bright. Things like Mercurian 421, they just go crazy. 3C279, they go crazy, especially in gamma rays. Our black hole just sort of burps a little bit. It has flares, but they're pretty modest in terms of energy and duration. Okay, so this is an artist's conception, obviously, not an actual image. So nustar is a spectroscopic telescope array, right? So besides taking images which are not quite Chandra-like in their beauty, it is studying in detail the X-rays as a function of energy that come out of different things, and in particular black holes. And so here it's looking at my personal favorite from my very beginnings in X-ray astronomy black hole, the very first black hole candidate, Cygnus X1. And they was observing it for, half a day. And so Cygnus X1 is about a 16 solar mass black hole in a binary with a big supergiant star. And it's secreting matter, and it's known to have a soft state and a hard state. The soft state means most of its emissions coming out at lower energy X-rays, and it'll switch states, and then you get to see closer into the black hole. I'm sure they'll go back and look at it again. But one of the things you can do is that there are very specific predictions from general relativity as to what a spectral line should look like as a function of the spin rate of the black hole. And so when you measure the line and you look at this line profile, maybe it's an iron line at 7,000 electron volts, or maybe it's a line that's, you know, at a different energy, but iron is traditionally used because it's very strong in most of these X-ray sources. Then you see what the line looks like, and you can actually measure how close to the critical spin rate the black hole is spinning. And so here's two different predictions of different line shapes. And a Schwarzschild black hole is a black hole that's not spinning, and a maximal Kerr black hole is a black hole that's spinning as fast as it possibly can spin without breaking up. Okay, so they're, you know, then they'll be studying this line and try to figure out, you know, which one of these shapes it looks more like, and, you know, be able to figure out the spin rate of the black hole. And so here's an example where they have already figured it out. This is a very big black hole in a distant galaxy, NGC 1365. And so with the help of nustar plus some other satellites, here's Suzaku, they were able to put the data together from 2 different satellites and measure the line shape and decide that the black hole spin rate was greater than 84% of the maximum spin rate.
What would determine the maximum?
It can't rotate any faster than that, or it would just fall apart, and that's hard to believe when it's a black hole.
But it would tend to, the centrifugal force would tend to dissipate, supposedly.
Yeah, so it's, you know, it's called a maximal Kerr black hole, and a Kerr black hole is a black hole that spins, and the equations of general relativity tell you it's only so fast it can spin. And so that's the maximal Kerr black hole.
That spin rate of 84%, is that 84% of the speed of light?
No, it's 84% of the maximum spin rate that you can have for a black hole of that mass. So that's one that they measured. And so here's an actual image that they took. Of course, the pretty image in the back is a visible light image. But when you look at this beautiful galaxy, which is IC 342, also known as Caldwell 5, when you look at that with X-rays, what you see are 2 different X-ray sources. Neither one of them are in the center of the galaxy, which is where the big black hole should be. Right? So that's weird. And so these are an example of what we usually call intermediate mass black holes, because they're too bright to be Cygnus X1 kind of black holes, but they're not big and in the center where they should be. If they were really big, heavy black holes, they would be in the center, right? Because all mass falls to the center of the galaxy. So that helps you figure out the mass of the black holes. Intermediate mass black holes are something like 100 to 1,000 solar masses. And we know how to make a black hole that's the mass of Cygnus X1, because that just comes from a really big star that blows up and leaves behind a big core. And there are lots of theories for how you make the really big black holes that are at the centers of galaxies, because they were probably formed when the galaxies were formed. But we don't actually have any clue whatsoever how you make a medium-sized black hole, because they're too big to have come from a star, and they're too small to have formed as part of the galaxy. And so, and then you think, well, maybe you could just collide a couple of Cygnus X1-sized black holes together, but they're never going to get close enough to each other to collide, so that doesn't work too well either. So they're a big mystery right now.
Is there something that tells you that those aren't just coincidental with this galaxy?
The fact that there aren't all that many X-ray sources in the sky compared to how many galaxies there are.
Okay.
So it is basically a statistical argument.
Okay.
But yeah, the X-ray sources are much fewer and far between than galaxies. And so when you see 2 in a galaxy, especially in regions where they're forming stars or, you know, bright active regions of the galaxy, then it's... I mean, I suppose if you did really good spectroscopy, you could look at redshifts of lines, but X-ray spectroscopy isn't that good. So you can't really do the distance that way.
I think I know where how the intermediate-sized black holes got there.
Oh, good. Read the paper and see if you can get it published.
Could it be that the galaxy, when it formed, could it be that it formed from the combinations of several smaller galaxies that had smaller black holes in them, and then when the two galaxies merged, the original core black holes from the original galaxies ended up sort of in random places rather than in the middle.
That would be a really nice theory, except for when galaxies merge, what happens is the pretty spiral galaxies all turn into boring elliptical galaxies. And as you can see, this is a pretty spiral galaxy.
Right.
And so that structure would have been destroyed by the merger, and you wouldn't have the pretty spiral galaxy anymore.
Oh.
So if this was a big elliptical galaxy, I might believe your theory.
There's no detectable black hole in the...
And then there's no detectable black hole in the center, which is even weirder. Because you know that, there probably really is a big one, it just must not be very active and eating anything that's making a lot of x-rays right now. So, I mean, you can see there's a bright point of light, right? But that doesn't, just because there's a bright point of visible light doesn't mean there's anything there that's 100 million degrees that would make an x-rays, right? It could be just a really cool one. It hasn't been accreting lately.
Is everyone in the professional community amazed? Because I'm amazed to see these things out in the office.
Black holes, well, I did a press conference where we first put forward the idea of intermediate black holes. I was running a press conference probably a good 20 years ago now. And people were like, oh no, that can't be right. And now, the more they look, the more they find evidence for these things. So I think it's pretty well established, but that doesn't mean that people have any really good clue as to where they're coming from. So here's some more. Now there's a mushy one, so you could be right about that galaxy. Right, so NGC 1313 on the side, and they can actually measure the masses of this one. This one closer to the center is 70, and this one out here is 30. And this one, I couldn't find the actual measurement of the masses. There's two in the source of this galaxy. This one is a big one right in the center. This is a supermassive black hole. And then here's the intermediate one out near the wings of the elliptical galaxy. So there's another one where your idea could possibly be correct. Okay, next subject, supernovae. All right, find the supernova. You guys are all experienced observers. The left is before and the right is after, so where's the supernova?
Right 6 o'clock.
Yeah, about 6.
Right there, right? Yeah. See, I knew you guys would all find it. Okay, so, and I'm sure you're familiar where supernovae come from at the end of the lifetime of a massive star. You're going to have a supernova. It's going to then either turn out to have nothing left over, in which case it just goes back and churns around and goes through one of these cycles again. Or you could have a small chunk left over and become a neutron star, or you could have a bigger chunk left over and become a black hole. Okay, in case anyone's wondering, the smallest size chunk you can have left over that could be a black hole is 3 solar masses. And all the neutron stars seem to be about 1.4. Okay, no one's ever seen a neutron star whose mass is not consistent with 1.4, which is the Chandrasekhar mass. Okay, and here's an animation. We'll see if this one works any better. All right, here's an animation of a supernova. Well, that one's working fine. Okay, so we're taking a little trip into the inner layers of the star, and we're traveling to the center of the star here. When we finally get there, we're going to see a bunch of different shells that are burning different elements. And so we have hydrogen burning into helium, and then we have helium burning into carbon, and carbon burning into other heavier things, and eventually it all stops when you get to iron, and then it runs out of all the fuel in its core, and then it collapses down, and then the outer layers get thrown off. And if you have enough of the core left over, you'll have a neutron star pulsar or something like that. Okay, so that's just a little artist's rendition. But here's an actual image of Cassiopeia A. Now, Chandra has done really spectacular images of Cassiopeia A that are so detailed that you can actually see the neutron star that was left in the middle, which isn't pulsing, as a little tiny dot. NuStar doesn't have quite that resolution, but the stuff that you see in blue is stuff that Chandra can't see. So these are the higher energy X-rays at the very outside. The green and the red light are the, excuse me, I'm trying not to sneeze here. The lower energy X-rays which overlap the Chandra band. And so Chandra really did a great job of imaging the middle, but you see the very outside is actually hotter, is actually the more energetic X-rays. And that's because as the supernova remnant expands, the shock front is at the outside edge. It's ramming into the gas in between the stars, and that's that shock is making the most heat, right? And then the inside is cooling as it's expanding, right? So the inside was hotter to start with, but as it expands out, the hottest stuff is at the outside edges where the shock occurs. And so here's a more detailed look, a little bigger, without it being overlaid on a visible light thing. And so it shows you the different energy of X-rays, and then the outside edges are harder. And then here's the even highest energy X-rays, and it's still the outside has the highest energy stuff. And don't forget, when you're seeing the middle, a lot of that is stuff coming towards you, right? So it's overlaid, because it's a sphere, it's not a circle, right? So you're seeing the shock in the front, right? But you mostly see it on the edges because it's just more, you're not having to look through the rest of the material. Okay, and now we're going to do narrow filter band imaging, just like you all do with H-alpha or whatever kinds of filters you guys like to put on your telescope. So this is the titanium 44 line. So this is a specific element that's coming out in that explosion from the inside of the star. This is everywhere there's titanium. And then the iron band, with the 7 keV iron band, is the red. And then the green is a different one. Well, it's just a continuum. Yeah, the iron band is 7, and this is just a wider band. And then the purple color is titanium. So you get to see the actual creation of an element, you know, exactly where it was in the star and where it went.
When you talk about the spin of a black hole, since a point mass doesn't have, the notion of spin doesn't apply, you're talking about the material inside the event horizon, or are you talking about the accretion disk outside the spin?
I'm talking about the actual black hole.
I mean the material inside the event horizon.
The black hole is the material inside the event horizon.
It's not a point mass.
Well, you're talking about singularity.
Right.
Yeah, no, it's, you know, the stuff inside the event horizon is, all of that is the black hole. The singularity is just a mathematical thing.
Right.
Okay. Right, because the black hole, the size of the black hole is the event horizon size. So it's not really a point mass, it's just the equations collapse to a point when you try to solve them.
But all the material inside the event horizon is not a point mass. It's
right, it's material inside the event horizon. Okay, so here's just a fun game if you want to try to play a game and learn more about supernova and stars. You students in the audience, you would like this game. It's a space mystery. It's called Solar Supernova. Check it out. It's fun. We have actually 4 other space mysteries at that website, mystery.cinema.edu. The first 3 have actual real videos, and the last 2 are cartoony, animated ones. So, but they all teach different ideas in space science. So, okay, well, what's more super than a supernova? A gamma ray burst. One of my favorite subjects. And so here we're starting with an even bigger star, 20 to 30 solar masses, and it's going to collapse all the way down to a black hole. So the chunk of stuff that's left over in the middle is going to be so big that you for sure end up with a black hole. So every gamma ray burst that we see, and we see about 1 a day somewhere in the sky, is the birth of a black hole somewhere in the universe. And nustar and all of my other satellites, Fermi and Swift, and not sure about XMM, saw a record-breaking burst on April 27th of this year, and we had a press conference about it a few weeks ago. It was longer and brighter than almost any burst we've seen to date, mostly because it was closer, and also because the jets that came out were aimed at us.
Do we have enough observing telescopes to sample the full sky, or is that?
We do. We have, on Fermi, there's the gamma ray burst monitor is an all-sky monitor. It's got 8 different cameras that cover the whole sky.
So one per
wide
day
field
is
camera.
what's happening in the observable unit.
Right. And so any gamma ray burst in general emits more energy in a few seconds than our sun puts out in its 10 billion year lifetime. So they're quite spectacular events. And this one was really, really bright and lasted a long time and made the highest energy gamma rays ever seen in a gamma ray burst. And so it was very exciting. So all the satellites got involved, and ground-based telescopes, because the ground-based telescopes know where Swift is going to be looking, They tend to always look in the part of the sky where Swift is looking, just in case they get lucky. And they actually were on this field of view of the sky before the burst happened, and so they got to actually see the rise of it in visible light, which is something that very rarely happens. Because normally you get a gamma ray burst, it puts out a blast on the internet that says, look at this place in the sky, and all the robotic telescopes slew and go over to that place in the sky, and they get there a minute or two later if they're good. You know, by the time the signal comes down and the telescopes get the signal and the telescopes slew, you usually have not caught the burst on the way up. But for some of these wide field of view telescopes like Raptor, which is run by Los Alamos, is the one, a lot of times they just look wherever Swift is looking, just in case they get lucky. And Swift has a pretty big field of view, Raptor has a pretty big field of view, and it's gotten lucky a few times that way. And so they were actually on this part of the sky and got to see the whole thing from start to finish.
Wow.
Which was tremendous wealth of data, especially because it turned out to be such a great burst.
How far away do they estimate this gamma ray burst was?
This one was actually fairly close. Do I have it on here? I don't think I have it on here.
In our galaxy, of course.
None of them are in our galaxy. They're all in other galaxies. The average distance to gamma ray bursts is 7 billion light years, and this one was only about 2 or 3, from what I recall. So close. Very close. Okay, so here's the artist's conception of it. There's Raptor on the ground. There's Fermi. There's Swift. Of course, if they were this close, they'd be getting blown up. There's nustar. This is going to be, without the telescopes on, it is going to be the cover image on Science Magazine in January sometime, if you get. And my artist did this, and so she's real excited she got another cover drawing. But we, of course, all like the one with the satellites on it better. Science made us take up all the satellites and telescopes. They just wanted to burst, because they put other stuff on the cover. Anyway, this is all of the different satellites and what they saw as a function of time. And this is a logarithmic scale on the bottom, so it's 1, 10, 100, 1,000, 10,000, 100,000 million seconds later. This is the brightness in visible light, from Swift's X-ray telescope, from Swift's gamma ray telescope, from Fermi's gamma ray burst monitor, from Fermi's large area telescope. So this is the highest energy gamma rays. Here's nustar, which got into the act a little bit late and kept following it. And so it's been a really interesting burst. We really learned a lot about it. For one thing, we learned that it really looks the same over a huge range of energies. It has the same sort of pattern in terms of the intensity falling off. Because from the visible light here at 2 electron volts to the Fermi Large Area Telescope, which is seeing energies over 1 billion electron volts, this thing was still making energy. This had the single highest energy photon ever seen in the gamma ray burst at 95 billion electron volts. One single photon.
Galaxy far away, what would the effect on the Earth be?
In order to actually fry the Earth, the gamma ray burst would have to be, a lot closer, like within our galaxy at about 3,000 parsecs. So, I don't know, 10,000 light years.
Is that,
So,
oh, excuse me, I'm sorry. Is that gamma ray that that powerful gamma ray, so powerful that it's the kind that can collide with a cosmic microwave background photon and get scattered off and can't exist anymore?
you don't actually need to have them be that high for them to do that. But it's around, usually somewhere around a GeV to 10 GeV is when they start interacting with the cosmic microwave background. So what Lou is referring to is if I was giving my Fermi talk, I would talk about this more, but there's a thing called the extragalactic background light. And so what happens is you've got a quasar really far away. The high energy gamma rays that would have been coming from it, you don't get to see because they interact with the cosmic microwave background photons and get scattered away. And so you don't get to see the really high energy photons from things if they're too far away. But this wasn't all that far away, compared to a lot of the quasars we're trying to study. And so, before Fermi was launched, nobody thought you could see photons that were more than a few MeV, so a few million electron volts from gamma ray bursts. Now we're seeing things at almost 100 billion electron volts. So clearly these are a lot more powerful than we would than we would have thought before. And so now we'll see how this animation works. This one is one that we did for the press conference. And so here we have our star. And now we're going to zoom in on the star. And then it's going to start sending out a jet as it starts to blow up. So here's a jet of particles coming out that are making light because they're accelerated charged particles. And then the jet is going to plow into some other stuff. And when you see purple, it's making gamma rays. So it's not quite there yet. So now it's just plowing into the interstellar medium and making a shock. And now the shock wave is heated up enough that it's making gamma rays. And now they're spinning it around so it faces you so you can see how bright it would be if you were looking right down the jet. And so that's the burst that we saw. And there it was on the sky map of all the other gamma ray things that were happening that day. So, I mean, this thing really stuck out like a sore thumb. So that is one of our animations. And here's our other one about jets. So here's our black hole in the middle sending out the jets from where the star used to be. And it's sending out stuff, and when the shells collide with each other, it makes gamma rays. And then when the shells collide with the external medium, it makes more gamma rays. That's called the external shock. That one's called the internal shock. And all the weird peaks and valleys we see in the gamma ray bursts are these colliding shells, because it's sort of not putting out the particles in a steady fashion. So that's what we've been studying with nustar. So we are trying to bring the high-energy universe into focus. We're getting sharper views and looking through the dust and gas into the centers of some galaxies. We're measuring some black holes. We're seeing some black holes nobody saw before. And this has all just been in 1 year. So it's been a really great year for nustar. And, you know, it's just getting started, so we can keep reading about more things that it's going to be doing in the future. And so I'll stop there, and I think we still have some time for questions. Although I really have no idea. We have lots of questions.
Pick a random galaxy. What's the expected time between gamma ray bursts?
Oh, well, considering that you only see one a day in the whole universe, and there's probably 10 billion galaxies, you know. And we've never seen one in our own galaxy. We've seen things that resemble gamma ray bursts, but they're not actually gamma ray bursts. So, you know, it's way too long for us to... You never see a second one from the same galaxy. That's never happened. Right? We've been seeing gamma ray bursts since the 1970s. So, I don't know, 50 or 60 years we haven't seen one repeat yet. And it's really going to be more like, you know, millions of years, I would say. So I'm not expecting to see another one.
What's the expected life of nustar?
Well, there's life and there's life, right? So the life of satellites depends on two things: how well they work and how much money NASA decides to keep giving you. It's working great. In this political climate, I don't want to hazard any guesses as to what's going to happen. It has no wheels or anything like Kepler did that are going to cause it to turn off prematurely. Although we are a little worried about Fermi because it has the same wheels as Kepler, but so far it hasn't had any wheel problems. SWIFT was launched in 2004 and they're still funding it, although the funding has been greatly reduced. nustar only had a nominally 2-year mission. And so it and all of my satellites and Kepler's new plans to try to revive itself with only 2 wheels are going into what's called the senior review in 2014 in January or February. And so all of the missions make their science case for an extended mission and why they should keep getting funded, and then NASA, in its infinite wisdom, decides how much money to give all of them and whether to turn off some of them or not. And so, but everything's working great, so, you know, if they keep funding it, it could easily last for 10 years. Ken?
Is the theory of X-ray and gamma ray emissions sufficiently well developed to allow you to tell something about the nature of the object that's emitting the X-rays or gamma rays, depending upon what the appearance of the spectrum looks like?
That depends on where you're looking at the spectrum. For gamma rays, it's a little tricky because we don't have very good spectral resolution, and almost everything looks like a e to the minus 2 power law.
Okay.
When you're up at that energy range, because it's all non-thermal emission, and non-thermal emission mostly always looks the same spectrally.
Right.
So in the case of X-rays, sometimes you see non-thermal and sometimes you see thermal. But when you see thermal emission, in other words, emission that's coming from the fact that it's a 100 million degree hot gas,
Right.
as opposed to emission coming from non-thermal things like accelerated charged particles and magnetic fields or gravitational fields.
Okay. All right.
When you're seeing thermal emission, then you get to see spectral lines.
Right.
And so then you can measure chemical elements. And so then you can tell things like, oh, this is a supernova remnant, or this is a cloud of gas in a cluster of galaxies. Right?
So
And
that's
so
most-
those have different signatures.
So that would, so thermal emission would most likely be, say, a supernova or something like that. Then.
Well, but you also see thermal emission from the inner rings of the accretion disks around the black
Right,
holes.
that's true,
Because
that's
those are
true.
100 million
Okay.
degree gas.
Is there a way to distinguish a black hole emission versus a supernova emission, or is it just a matter of
Well, with the supernova,
supernova
you see a
emission
lot of
doesn't
these,
be a
you
rise
see
and
a lot
fall,
of these
right?
lines.
Exactly.
Well, that's the light curve, right? So
Right.
there's the pattern of the intensity of the light versus time. Of
Right.
course, that tells you a tremendous amount, because
Right,
that's a
right.
burst, or that's a flare, or that's a pulsar, right?
Right, right.
But then there's the intensity of the light versus energy. That's the spectra,
Mhm.
and there it gets a lot more subtle.
Okay.
Right, if you see chemical lines or nuclear lines, then you've learned a lot. If you just see a flat power law, there's a whole lot of things that make flat power laws just
Right.
a straight line, that goes down with the slope of -2.
So that'd be much harder. Right.
Then it's really hard, and then you have to look at other contexts. And usually, what you do is you look in lower energy wavelengths where you get prettier pictures, and you can say, "Oh, that's a galaxy." That's
Okay. Sure. Right.
You can see
right.
what's there.
Sure. Okay.
I have a real basic physics question about what you've been talking about. You keep talking about chemical lines. Right, so we're talking, like if you have some element
Well,
like...
they're really
Well,
mostly nuclear lines, but...
they're nuclear
Well,
lines.
for nustar, yeah.
Okay, so these are nuclear states that are collapsing in... Okay.
Yeah, but you also see, the iron line is a chemical line. So, but it's
This is like a really high energy electron that's collapsing?
So iron normally has 26 electrons. And what you're seeing is 25 times ionized iron.
Wow.
And you're seeing that electron go in that last little, the last electron being ripped off takes X-ray energies to do it.
Yes.
Okay.
The outer ones come off very easily and would make visible light spectral lines, and then the next ones would
But
make
it is-
ultraviolet lines. And by the time you get to that last electron that's bound to that iron nucleus, it takes X-ray energies to pull it out. And so those are chemical lines. But they're coming out in X-rays instead of coming out in visible or infrared like you guys are used to.
I'm enrolled at Dominican for an adult-based astronomy program.
Good for
I don't
you.
know if you're familiar with it, but
I know nothing
does
about
Sonoma
it.
State offer anything like that?
We have the Osher Lifelong Learning Institute, and courses are in different subjects all the time. I'm not aware of one that's in astronomy for this next semester. There are all sorts of different interesting ones, though. And I guess they have 3 different semesters a year, and the classes are 6 to 8 weeks long, and there's no homework and no tests, from what I understand, so that's very appealing to adult learners. Because we're done with tests, right? We've already had enough tests in our lives.
What was the advantage of launching from the plane?
One of the advantages was they wanted to be in an equatorial orbit. And we don't have any launching platforms for big rockets anywhere on the equator anymore. A long time ago, when I first got into the X-ray astronomy business, the first satellite I worked on and the second satellite I worked on were both launched on a launching platform off the coast of Kenya called San Marco. And that was put you into an equatorial orbit. Now, why do you want to be in an equatorial orbit? What's wrong with the Cape Kennedy orbit, which is 28 degrees, or what's wrong with the Vandenberg orbit, which is almost polar? Well, in X-ray astronomy, X-ray detectors are sensitive to X-rays, but they're also, and gamma ray detectors are sensitive also, to particles, charged particles, in things like the Van Allen belts, and at the magnetic north and south pole, where If you've ever seen a picture of your magnetic field, it looks sort of like a butterfly, and all the field lines come in and the magnetic poles, right? And so you don't want to fly through the polar regions because there's a big concentration of charged particles there that will set off your detectors. But what people didn't know is that there are also 2 other spots on the Earth where the Van Allen belts dip down and there's lots of charged particles there, and the satellites try to avoid those areas, and one's in the North Pacific and one's in the South Atlantic. And they're called the North Pacific and the South Atlantic anomalies. And so, if you're flying on the equator, you avoid those other places where those 2 radiation things are. And so you have a much lower background and a much cleaner signal. So that's why an equatorial orbit is actually the ideal thing. 28 degrees is not bad. You know, it's a shuttle orbit is low, but I mean, at 28 degrees, which is what you end up when you launch from Florida, is not a bad orbit to be in, but equatorial is really the best from the point of view of X-ray and gamma ray astronomy because of those radiation problems.
How do they get the stationary satellites launched? They're in orbits, aren't they?
You mean the geosynchronous satellites?
Yeah.
Well, those are parked over a particular place on the Earth, so they're not in, they're not in an equatorial orbit. They're in the orbit of the place on the Earth that they're at. Okay. And they're way the heck out. They're not in these are all low Earth orbits that are every 90 minutes.
But I mean, where are they launched from?
They're basically launched with many stage rockets because they've got to get way the heck up there compared to these low Earth orbits. So Iranian rockets, Russian rockets, anybody can launch those, but they've got to have much more complicated booster patterns to get them all the way out there, and then they park.
So how did you enjoy visiting Kwajalein?
I did not get to go.
Oh.
No, I did not. I've gone to Cape Kennedy for launch of Swift and Fermi, but I did not get to go, or Cape Canaveral. I did not get to go to Kwajalein, and I'm sort of not minding it. Even Fiona Harrison, the principal investigator for nustar, did not go to Kwajalein for the launch. She sat in Berkeley in the control room, and she let some tough guys go there and camp out. It's not a very hospitable place. I think only maybe 4 people went to go with it, besides the actual launch crew, for the scientific support people.
Nice.
How many intermediate black holes have been detected?
I'd say there's probably about a dozen now.
All the various.
Yeah, that are well established. And so, part of the problem is
still theoretical. I mean,
there's a correlation between the size of the black hole and the maximum luminosity it can be expected to have. It's called the Eddington limit. And so, one of the major reasons people think that they weigh more is because they're too bright to be a normal-sized black hole and have that intensity. And so, that's the other way around it. Somehow there could be something wrong with the whole Eddington limit idea, physics-wise. So another thing people call them besides intermediate mass black holes is ultraluminous X-ray sources. Because they're too bright, they shouldn't be able to be that bright.
And you said there's no way that they would collide with the central.
People get this opinion by watching movies probably that things in space actually can collide often and touch each other. Never happens. There's so much space in space, right?
Far more space than
you don't go zooming through the asteroid fields on your rocket ship dodging asteroids. That doesn't happen either, right? Well, just like when 2 galaxies collide, as we were talking about before, nothing actually collides. Right?
Yes.
All the things just pass through each other, right? None of the stars collide, the 2 black holes don't collide. They all affect each other with the gravity, but they basically just sort of pass through each other and distort the shapes of each other. But nothing actually hits anything, because almost everything in the galaxy is just space.
Yep.
And so nustar is an array. It's considered an array because
it has 2 telescopes. Of course, originally it had 3 before they cut the budget, so it was a bigger array. But it has 2 co-aligned telescopes. So it's an array of telescopes. It's not just one telescope.
Well, you showed us an image of the sensor.
And the sensor, yeah, there is a pixel array in each focal plane. So it has 2 focal planes and 2 telescopes.
Oh, okay.
So that's true too.
I want to present you with yet another.
Oh, thank you.